Right now, trillions of particles are passing through your body. Neutrinos from the sun, photons bouncing off every surface, electrons flowing through your nerves. You probably imagine each one as a tiny object, a little sphere flying along a definite path from one place to another. That picture feels natural. It feels obvious. But here is the thing. That picture is wrong. Not slightly wrong, fundamentally wrong. Before you measure a particle, before any interaction forces it to reveal a definite property, quantum physics says it does not have one. Not because we lack information, not because our instruments are too crude, but because the particle genuinely does not possess a definite position or a definite speed in the way a ball or a bullet does. So if it is not a tiny object with a fixed path, what is actually there? That question has haunted physics for a century, and the answer changes everything. If you find these deep questions about reality fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Let us start with something that seems completely obvious. Pick up a coin from a table, hold it between your fingers. You know exactly where it is. You know it has a definite shape, a definite weight, a definite temperature. If you toss it, you can watch its arc through the air. At every instant during that arc, the coin is somewhere specific. It has a position. It has a speed. It has a direction. These things are all true at the same time, and if you had perfect information about every force acting on that coin, you could predict exactly where it would land. This is how the physical world works at the scale of everyday life. Objects are things. They have definite properties at every moment. They follow definite paths through space. And if you are clever enough, you can track those paths precisely. This intuition runs so deep that most people never question it. It feels like a fact about reality, not a belief. Of course, a baseball has a position when no one is looking. Of course, the moon is orbiting Earth right now, even if no one is staring at it through a telescope. Of course, every object in the universe has definite properties at every moment in time, whether or not anyone happens to be checking. This intuition has a name. It is called classical mechanics, and for centuries it was the undisputed king of physics. Isaac Newton built its foundations in the late 1600s. His laws of motion and his law of universal gravitation described how objects move under the influence of forces with such precision that scientists could predict the motion of planets decades in advance. Newton's framework told you that if you know where every particle in the universe is right now, and how fast each one is moving, you can, in principle, calculate the entire future of the universe. Every collision, every orbit, every trajectory, all determined by the current state. The universe in Newton's picture is like a vast clockwork machine. Set the initial conditions, wind it up, and everything that follows is inevitable. This was not just a useful tool, it became a worldview. Reality at its deepest level was made of objects with definite properties, following definite paths through a definite space, under the influence of definite forces. Everything was determined. Everything was precise. Everything was knowable, at least in principle. And this framework worked spectacularly well. Engineers used Newtonian mechanics to build bridges, design engines, and eventually launch rockets into space. Astronomers used it to predict eclipses, discover new planets, and calculate the trajectories of comets. The entire Industrial Revolution was built on the assumption that the physical world is made of definite objects, obeying deterministic laws. So it made perfect sense, when scientists began discovering the building blocks of matter, to assume those building blocks were just smaller versions of everyday objects. Tiny spheres with definite positions and definite velocities, following definite paths through space, obeying the same deterministic laws as everything else. The idea that matter is made of tiny indivisible units goes back a very long time. Around 400 BC, Greek philosophers Leucippus and Democritus proposed that if you kept cutting a piece of material into smaller and smaller pieces, you would eventually reach something that could not be cut any further. They called these smallest pieces atoms, from the Greek word meaning uncuttable. Everything in the world, they argued, was made of atoms moving through empty space, colliding and combining to form the structures we see around us. It was a brilliant intuition. But for nearly 2,000 years, it remained just that, an intuition. There was no way to test it, no way to see atoms, no way to prove they existed rather than matter being infinitely divisible, as Aristotle had argued. The modern atomic theory began to take shape in the early 1800s. John Dalton, an English chemist, studied how elements combine in chemical reactions and noticed something striking. They always combined in fixed ratios by mass. Hydrogen and oxygen always combined in the same proportion to form water. Carbon and oxygen always combined in the same proportion to form carbon dioxide. This made perfect sense if matter consisted of discrete units, atoms, each with a specific mass. Dalton's atomic theory gave chemistry a foundation, but atoms at this stage were still imagined as tiny solid spheres, little billiard balls, classical objects at a very small scale. Then, near the end of the 1800s, things started to crack. In 1897, J.J. Thomson discovered the electron. He showed that atoms were not indivisible after all. They contained smaller, negatively charged particles. This was a surprise. If atoms have internal structure, they are not truly uncuttable. Thomson proposed a model where the atom was a ball of positive charge with electrons embedded in it, like raisins in a pudding. Then, in 1911, Ernest Rutherford fired alpha particles at thin gold foil and found that most passed straight through, but a few bounced back at sharp angles. This only made sense if the atom's positive charge and nearly all its mass were concentrated in a tiny core, the nucleus, about 10,000 times smaller than the atom itself. The atom was almost entirely empty space, with a dense central nucleus and lightweight electrons orbiting far away. Niels Bohr refined this picture in 1913. He proposed that electrons orbit the nucleus in specific allowed orbits, jumping between them by absorbing or emitting light. His model successfully predicted the colors of light emitted by hydrogen. But even Bohr's model still treated the electron as a tiny particle orbiting the nucleus, like a miniature planet orbiting a star. The electron had a definite position on its orbit at every moment. It traced a definite path around the nucleus. It was still, fundamentally, a classical object, following classical rules. Just a very small one. This is the picture most people still carry around in their heads. Atoms are tiny solar systems. Electrons are little balls zooming around a nucleus. Particles are small objects with definite locations and definite paths. And for a long time, scientists carried this picture too. But nature had other plans. And the experiment that shattered this picture is one you may have heard of, though its full implications are more shocking than most people realize. In 1801, an English scientist named Thomas Young performed one of the most elegant experiments in the history of physics. He took a beam of light and directed it at a barrier with two narrow slits cut into it. Behind the barrier, he placed a screen. If light were made of tiny particles, little bullets flying through the air, you would expect to see two bright bands on the screen, one behind each slit. Each particle would fly through one slit or the other and hit the screen directly behind it. That is what classical particles do. They go through one opening or the other and pile up accordingly. But that is not what Young saw. Instead, the screen displayed an interference pattern, a series of alternating bright and dark bands spread across a wide area. This is what waves do. When two sets of waves overlap, they can reinforce each other where crest meets crest, creating bright bands, or cancel each other where crest meets trough, creating dark bands. Ocean waves do this when two sets of ripples cross each other. Sound waves do this when two speakers play the same tone and you hear loud and quiet spots in the room. Young's experiment showed that light behaves like a wave. The light passing through one slit interferes with the light passing through the other slit, producing the characteristic pattern. This seemed to settle the question. Light is a wave, not a stream of particles. For the next century, wave theory dominated. James Clerk Maxwell showed in the 1860s that light is an electromagnetic wave, a ripple in electric and magnetic fields propagating through space. This explained reflection, refraction, diffraction, and interference, all in one beautiful framework. Light had a wavelength, a frequency, and an amplitude. It spread out, bent around corners, and interfered with itself. Everything a wave should do. The case seemed closed. Light was a wave. Period. But then, in 1905, Albert Einstein complicated the picture. He showed that light, when it interacts with matter, behaves as though it comes in discrete packets, individual units of energy. These packets were later called photons. The evidence came from the photoelectric effect. When light hits a metal surface, it can knock electrons loose. But the way this works defied every prediction the wave theory made. If light were purely a wave, you would expect that brighter light, meaning a more intense wave, would always knock electrons loose, and that dimmer light would struggle. It would be like ocean waves hitting a dock. Bigger waves push harder, smaller waves push less. But that is not what experiments showed. Dimmer light of a high frequency knocked electrons loose easily. Brighter light of a low frequency did not knock any loose at all, no matter how intense the beam was. It did not matter how long you shone the low-frequency light. It did not matter how powerful the source was. Nothing happened. The electrons stayed put. But the moment you switched to a higher frequency, even at very low intensity, electrons flew off the surface immediately. Not after a delay while the wave built up energy. Immediately. One photon at a time. Einstein explained this by proposing that light energy arrives not as a continuous wave, but in discrete chunks. Individual photons, each carrying a specific amount of energy, determined by their frequency. A high-frequency photon carries enough energy to eject an electron. A low-frequency photon does not, no matter how many of them you send. Each interaction is between one photon and one electron. The energy transfer is all or nothing. This was particle-like behavior, unmistakably particle-like, arriving in lumps, transferring energy in discrete amounts, behaving like tiny bullets of light. So light is a wave. Young proved it with interference. Maxwell described it mathematically. And light is also a particle. Einstein proved it with the photoelectric effect. Both descriptions are correct in different experimental contexts. This was profoundly unsettling. For centuries, waves and particles were considered completely different things. Waves spread out, interfere, and are continuous. Particles are localized, follow definite paths, and are discrete. Light seemed to be both at once, which was like saying something is simultaneously dry and wet. Physicists did not know what to make of it. Some tried to reconcile the two pictures. Others hoped the contradiction would resolve with better experiments. It did not. It got worse. In 1924, a French physicist named Louis de Broglie made an extraordinary proposal. If light, traditionally thought of as a wave, also behaves as particles, then perhaps matter, traditionally thought of as particles, also behaves as waves. De Broglie suggested that every particle, electrons, protons, atoms, even baseballs, has an associated wavelength. The wavelength depends on the particle's momentum. The faster and heavier the particle, the shorter the wavelength. For everyday objects like baseballs, the wavelength is so impossibly small that wave behavior is completely undetectable. A baseball's de Broglie wavelength is roughly 10 to the negative 34 meters. That is comparable to the Planck length. There is no experiment that could ever detect wave behavior in a baseball. But for tiny particles like electrons, the wavelength is large enough to matter. An electron moving at typical speeds inside an atom has a wavelength of roughly 1/10 of a nanometer, comparable to the size of the atom itself. At that scale, wave behavior is not just detectable, it dominates. Du Bois' idea was confirmed experimentally in 1927 by Clinton Davison and Lester Germer, who fired electrons at a nickel crystal and observed a diffraction pattern. The electrons were behaving like waves, diffracting off the crystal lattice the same way X-rays do. Electrons, particles of matter with mass and charge, exhibited wave behavior. This was no longer just strange, it was a full-blown crisis. Light behaves as both wave and particle. Matter behaves as both wave and particle. The two categories that physics had relied on for centuries, wave and particle, were no longer separate. Everything seemed to be both at once, depending on how you looked at it. No one had a framework for understanding this. No one had a theory that could accommodate an object being simultaneously localized and spread out, simultaneously discrete and continuous. The classical world was built on an either-or distinction. Something is a wave or a particle. Nature was saying neither, or both, and nobody knew what to do with that. Now, here is where the double-slit experiment becomes truly disturbing. Imagine repeating Young's experiment, but instead of using a beam of light, you use a beam of electrons. You fire electrons at a barrier with two slits and detect where they land on a screen behind it. Each electron that hits the screen registers as a single point, a single dot, just like a particle. There is no smearing. Each electron arrives at one specific location. But as more and more electrons hit the screen, one by one, a pattern begins to emerge. And that pattern is not two clusters behind the two slits. It is an interference pattern, alternating bands of many hits and almost no hits. The same pattern you see with waves passing through two slits. This was confirmed with extraordinary clarity in a landmark experiment performed in 1989 by Akira Tonomura and colleagues at Hitachi. And the way they did it makes the result even more staggering. They sent single electrons, one at a time, through a double-slit apparatus. One electron at a time. Not a beam, not a flood. A single electron, completely alone, with no other electrons anywhere near the apparatus. There was no possibility that one electron was interfering with another. There was only one electron in the experiment at any given moment. Each electron hit the detector screen and registered as a single dot, a tiny flash at one specific location. If you looked at the screen after just the first 10 or 20 electrons, you would see nothing meaningful, just a handful of random dots scattered across the surface. There was no hint of order, no pattern, no structure, just randomness. It looked exactly like what you would expect if tiny particles were flying through the slits and landing wherever they happened to land. But the researchers kept going. They let the experiment run, electron after electron, dot after dot. After a few hundred electrons, something started to happen. Faint structures began to emerge from the noise. Certain areas of the screen were getting more dots than others, not dramatically, but noticeably. It was still hard to tell if this was a real pattern or just statistical fluctuation, but the researchers kept going. After thousands of electrons, the pattern was unmistakable. Bright bands where many electrons had landed, dark bands where almost none had. The dots were not filling in uniformly. They were organizing themselves into alternating stripes. After tens of thousands of electrons, the pattern was textbook perfect. A full interference pattern. The exact pattern you would expect from waves passing through two slits and interfering on the other side. Bright where crest meets crest, dark where crest meets trough. Beautiful, regular, undeniable. But there were no waves in the traditional sense. There was only one electron at a time. It had nothing to interfere with. Each electron arrived alone, registered as a single dot, and was gone before the next one was fired. And yet, over many trials, the collective pattern was wave-like interference. Each individual electron behaved like a particle, landing at a single point. But the collection of many individual particles produced a pattern that only waves can create. This is the result that breaks classical physics. If each electron is a tiny particle that goes through one slit or the other, like a bullet, then each electron should land behind one slit or the other. You should see two clusters on the screen, two bands, no interference. To get an interference pattern, you need something passing through both slits simultaneously and interfering with itself on the other side. But each electron is detected as a single particle at a single point. It does not arrive at two places at once. It arrives at one specific location. So what is happening between when the electron is emitted and when it is detected? Here is where classical thinking completely collapses. You might say, fine, the electron is a particle and it goes through one slit. We just cannot predict which slit. That would give two bands, not an interference pattern. You might say the electron is a wave and goes through both slits. But waves do not land at single points. Waves spread out and hit the screen everywhere. The electron does land at a single point every time. You might say the electron somehow splits, half going through each slit, then recombines. But no experiment has ever detected half an electron. The electron's charge is always the full charge. Its mass is always the full mass. It does not split. The situation gets even more bewildering when you try to watch which slit the electron goes through. If you place a detector at one of the slits, something that records whether the electron passed through slit 1 or slit 2, the interference pattern vanishes completely. You get exactly the two-band pattern you would expect from classical particles going through one slit or the other. The act of gaining which path information destroys the interference. And here is what makes this even more unsettling. When the detector is in place, it does not show anything ambiguous. It does not show the electron going through both slits. It does not show the electron spread out or split in two. It shows the electron going through one slit, every single time. Slit 1 or slit 2, never both, never neither. A perfectly definite, classical-looking result. The electron behaves exactly like a tiny bullet. It picks a slit and goes through it. And on the screen behind, the pattern confirms this. Two bands, one behind each slit. Exactly what you would expect from classical particles following definite paths. So when the detector is present, the electron appears to be a classical particle with a definite trajectory. When the detector is absent, the electron produces an interference pattern that is impossible for any classical particle to produce. The same electron, the same slits, the same screen. The only difference is whether or not a piece of information, which slit it went through, is recorded anywhere in the physical world. The presence or absence of that information changes what the electron does. Not what we know about what it does, what it actually does. Remove the detector so that no which path information exists and the interference pattern comes back. Put the detector back and the pattern disappears again. You can toggle the interference on and off simply by choosing whether or not to gather information about which slit the electron passes through. The electron's behavior depends on whether or not it is possible, even in principle, to know which path it took. Not on whether you personally looked at the result, not on whether a human being was involved, but on whether the information exists anywhere in the physical world. Richard Feynman, one of the greatest physicists of the 20th century, called this the central mystery of quantum mechanics. He said that this single experiment contains the only mystery. Everything else in quantum physics is a variation of the same theme, and he was not exaggerating. Because this experiment is not just showing us something strange about electrons, it is showing us something fundamental about the nature of physical reality before measurement. Think carefully about what the double-slit experiment is telling us. Before the electron hits the screen, before it is detected, it does not have a definite path. It did not go through slit 1, it did not go through slit 2, and it did not go through both. The question, which slit did it go through, has no answer. Not because we do not know the answer, but because there is no answer. The electron does not have a definite trajectory. The concept of a definite path simply does not apply. The electron, between emission and detection, is not a classical object. It is not a tiny ball flying along a specific route. It is something else entirely. Something the classical framework has no language for. And this is not a peculiarity of electrons. The same experiment has been performed with photons, neutrons, atoms, and even large molecules. In 2019, researchers performed double-slit interference with molecules containing over 2,000 atoms, objects large enough to be seen with an electron microscope. Even these relatively huge molecules produced interference patterns when no which path information was available. The phenomenon is universal. Every quantum object, no matter how large, behaves this way. The classical picture of particles as tiny objects with definite positions and definite paths is not just incomplete. It is wrong at the most fundamental level. This was the crisis that confronted physics in the 1920s. The experiments were clear. Particles do not behave like classical objects. They do not follow definite paths. They exhibit interference, which requires something like wave behavior. Yet they are detected as individual localized events, which requires something like particle behavior. Neither the classical particle picture nor the classical wave picture captures what is actually happening. Reality at the quantum scale does not fit into either category. And this was not a failure of imagination or a failure of technology. It was a failure of the classical worldview. The assumption that every object has definite properties at every moment, that every object follows a definite path through space, that reality is made of things with determined states, this assumption is simply not true at the quantum scale. The double-slit experiment proves it with devastating clarity. If particles had definite paths, you would never see interference from single particles. If particles were waves in the ordinary sense, you would never see single localized detection events. Neither picture works. Something entirely new is required. That something new arrived in the 1920s, and it did not look like anything physicists expected. It did not offer a comfortable picture of tiny objects following precise trajectories. It did not offer a reassuring clockwork universe where everything is determined and predictable. Instead, it offered something far more radical. A mathematical framework that predicts the probabilities of measurement outcomes with extraordinary precision, but refuses to tell you what the particle is doing between measurements. The framework works. It has never failed an experimental test in nearly 100 years, but it demands that we give up the most basic assumption of classical physics, that things have definite properties when no one is looking. That framework is quantum mechanics, and what it says about what a particle is before you measure it is profoundly different from anything the classical world prepared us for. The next step is to understand exactly what quantum theory says about a particle's state before measurement, why it is not simply a matter of ignorance, and why the quantum description is far stranger and far more precise than the classical picture it replaced. Because the double-slit experiment did not just destroy the old picture, it pointed the way toward a new one. A description of reality that is mathematically rigorous, experimentally confirmed, and genuinely unsettling in what it tells us about the nature of existence. The coin on your table has a definite position. The electron passing through the double slit does not. And that difference is not a small technical detail. It is a revolution in our understanding of what the physical world actually is. So the double-slit experiment destroyed the classical picture. Particles do not travel along definite paths. They do not have definite positions between measurements. The comfortable image of a tiny ball flying through space, carrying all its properties with it like luggage, is wrong. But physics does not simply tear down old ideas and leave nothing in their place. In the 1920s, physicists built something new, a mathematical framework so precise, so powerful, and so deeply strange that it has survived every experimental test thrown at it for nearly 100 years. That framework is quantum mechanics. And what it says about a particle before measurement is not vague. It is not hand-waving. It is one of the most exact and rigorous descriptions in all of science. But it demands that we accept something profoundly uncomfortable. Let us build up to it carefully. In classical physics, describing a particle is straightforward. You give its position and its velocity. That is the complete description. If you know where a baseball is, and how fast it is moving, and in what direction, you know everything there is to know about that baseball's motion. You can predict its entire future trajectory. You can calculate where it will be 1 second from now, 10 seconds from now, 100 years from now, if nothing disturbs it. The state of a classical particle is just a list of numbers, position and velocity. Simple, definite, complete. Quantum mechanics replaces this with something entirely different. Instead of a position and a velocity, the complete description of a quantum particle is something called a quantum state. Physicists write it using a mathematical object called a wave function, usually denoted by the Greek letter psi. The wave function is not a simple list of numbers. It is a mathematical function that assigns a complex number, a number with both a real and an imaginary part, to every point in space. It is spread out. It exists everywhere the particle might be found. And it encodes everything quantum mechanics can possibly tell you about the particle. Now, what does this wave function actually mean? This is where things get subtle, and where many popular explanations go wrong. The wave function is not a physical wave, like a water wave or a sound wave. You cannot see it. You cannot touch it. It does not ripple through some medium. It is a mathematical object that lives in an abstract mathematical space. But it is not merely a bookkeeping device either. It has physical consequences. It determines, with extraordinary precision, what you will observe when you perform a measurement. Here is how it works. Suppose you have an electron and you want to know where it is. You perform a position measurement. Before you measure, the wave function of the electron is spread across a region of space. It might be concentrated mostly in one area, but have small values extending outward in all directions. When you actually perform the measurement, you find the electron at one specific location, a single definite point. Not spread out, not smeared, a definite position. But which position? Quantum mechanics says you cannot predict exactly where you will find it. What you can predict is the probability of finding it at each possible location. And those probabilities are determined by the wave function. The rule connecting the wave function to probabilities is called the Born rule, named after Max Born, who proposed it in 1926. The rule says that the probability of finding the particle at a given location is proportional to the square of the wave function's amplitude at that location. Where the wave function is large, the probability is high. Where the wave function is small, the probability is low. Where the wave function is 0, the probability is 0. You will never find the particle there. This might sound like the wave function is just describing our ignorance. Maybe the electron actually is at a specific location, and the wave function simply reflects the fact that we do not know which location. Like a weather forecast that says there is a 70% chance of rain. The rain will either happen or it will not. The 70% just reflects our lack of information. Many people hear about quantum mechanics and assume this is what is going on. The particle has a definite position, we just do not know it, and the wave function is our best guess. But that is not what quantum mechanics says, and the double-slit experiment is the proof. Remember what happened. Single electrons, fired one at a time, produced an interference pattern. If each electron had a definite position and followed a definite path through one slit or the other, you would see two bands on the screen, not interference. The interference pattern only appears if something goes through both slits simultaneously and interferes with itself. If the electron had a definite position at every moment during its flight, it would go through one slit. It would have a definite path, and interference would be impossible. The fact that interference occurs proves that the electron does not have a definite position between emission and detection. The wave function is not describing our ignorance of a definite reality. It is describing a reality that is genuinely indefinite. This is the hardest thing to accept about quantum mechanics, and it is worth pausing on. In everyday life, when you do not know something, the thing you do not know still has a definite value. If you flip a coin and cover it before looking, the coin is either heads or tails. Your ignorance does not change that. The coin has a definite state. You just do not know what it is. In quantum mechanics, this is not the case. Before you measure an electron's position, the electron does not have a definite position. It is not heads or tails under a cover. The question, "Where is the electron?" has no answer. Not because you lack information, but because the electron is in a state where position is genuinely undefined. This state is called a superposition, and superposition is not a metaphor. It is not a way of saying we are confused. It is a precise mathematical description of a situation where a particle exists in a combination of multiple possible outcomes simultaneously. Not one or the other. Not secretly one with us, unable to tell. A genuine combination. The wave function of the electron encodes this superposition. When the wave function has significant values at many different positions, the electron is in a superposition of being at many different positions. None of those positions is the real one. They are all part of the quantum state equally. This becomes vivid when you think about a specific property that is even simpler than position. Quantum particles have a property called spin. For an electron, spin is a bit like a tiny internal compass needle. When you measure it along a chosen direction, you always get one of exactly two results. You might call them spin up and spin down. There are no other options. Every measurement gives one or the other. Now, suppose you prepare an electron so that its spin along the vertical direction is definitely up. If you then measure its spin along the vertical direction, you will always get up. 100% of the time. No surprise. But now measure its spin along the horizontal direction instead. Quantum mechanics says you will get left or right with equal probability. 50-50. And here is the crucial point. Before you make that horizontal measurement, the electron's horizontal spin is not secretly left or secretly right. It genuinely does not have a definite horizontal spin. It is in a superposition of left and right. The vertical preparation created a state that, with respect to the horizontal direction, is fundamentally indefinite. This has been tested countless times. The Stern-Gerlach experiment, first performed in 1922, sends particles through a magnetic field that separates them according to their spin. Decades of variations on this experiment have confirmed quantum predictions to extraordinary precision. The results always match what quantum mechanics predicts, and they are incompatible with the idea that the particle secretly had a definite spin all along. So the quantum state, the wave function, is not a description of what we know. It is the most complete description of the particle that exists. There is nothing more to know, no hidden information that would tell you exactly where the electron is or exactly which spin it has. The quantum state is all there is. This is what physicists mean when they say the quantum state is the complete physical description. It is not incomplete. It is not an approximation. It is the actual state of the physical system, and that state simply does not assign definite values to certain properties. The indefiniteness is not in our knowledge, it is in nature. Now let us talk about what happens when you do measure. This is where the second strange feature of quantum mechanics appears. Before measurement, the electron is in a superposition. Its wave function is spread out, encoding probabilities for many possible results. When the measurement occurs, something happens. One definite result is obtained. The electron lands at one specific point on the detector. The spin measurement gives one specific outcome. The superposition is gone. The wave function has changed. Before the measurement, there were many possibilities. After the measurement, there is one actuality. This transition from many possibilities to one actual outcome is one of the deepest puzzles in physics. In the standard formulation of quantum mechanics, it is described by a rule. When a measurement is performed, the wave function collapses to a state corresponding to the observed result. If you measure position and find the electron at a specific point, the wave function suddenly becomes concentrated at that point. If you measure spin and get up, the wave function becomes the spin-up state. This collapse is instantaneous and irreversible within the standard formalism. Before the measurement, many outcomes were possible. After, only one occurred. Let us walk through what this actually looks like, concretely. Imagine you have prepared an electron in a quantum state where the wave function is spread across a region about 1 millimeter wide. That is actually quite large for quantum mechanics. The electron has no definite position within that millimeter. The wave function has significant values at every point across that entire region. Now you bring in a detector, a small device designed to register where a charged particle strikes it. The detector is made of atoms, trillions upon trillions of them, all interacting with each other and with the surrounding environment. The electron's wave function reaches the detector, and something happens. One atom in the detector absorbs energy. That atom was at one specific location. The absorption triggers a cascade. Electrons are knocked free. A current flows. An amplifier registers the signal. A dot appears on a screen. The electron was found here, not there, not spread across the whole millimeter, here, at this one point. A moment ago, the quantum state assigned no special status to that point. It was one possibility among a continuous infinity of possibilities. The wave function was just as large a tiny fraction of a millimeter to the left or to the right. There was nothing in the quantum state that said this point would be the one. No flag, no marker, no indication that this location was destined to be the outcome. And yet, when the measurement occurred, this one point became the reality. Every other possibility vanished. The wave function, which a moment ago was spread across a millimeter, suddenly became concentrated at a single location. If you repeat the experiment with an identically prepared electron with exactly the same wave function spread across exactly the same millimeter, you will get a different result. The dot will appear somewhere else. Still within that millimeter, still at a location where the wave function was large, but not at the same point. Run the experiment 1,000 times, and you will get 1,000 different points, scattered across the millimeter in a pattern that matches the shape of the original wave function. Where the wave function was large, many dots cluster together. Where it was small, few dots appear. The Born rule is confirmed with exquisite statistical precision, but each individual result is random. Genuinely, fundamentally random. This is what makes the measurement transition so jarring. It is not like gradually zooming in on something that was always there. It is like a sudden snap. Before the measurement, a spread-out quantum state with no definite position. After the measurement, a sharp, definite outcome at one specific point. The formalism describes this transition with a single rule, but the transition itself is one of the strangest things in all of physics. But here is what is very important to understand. Quantum mechanics does not tell you which outcome will occur. It only tells you the probabilities. For any given measurement, the theory predicts the likelihood of each possible result, and those predictions are spectacularly accurate. If quantum mechanics says there is a 30% chance of finding the electron in a certain region, and you repeat the experiment thousands of times, about 30% of the time you will find it there. The statistics match the predictions with extraordinary precision. But for any single measurement, the outcome is fundamentally unpredictable. This unpredictability is not like the unpredictability of a coin flip. A coin flip is unpredictable in practice because you do not know the exact forces on the coin. But in principle, if you knew the exact initial conditions, you could predict the outcome. The physics is deterministic. The unpredictability is just a reflection of your ignorance. In quantum mechanics, the unpredictability is fundamental. Even if you know the quantum state perfectly, with every detail specified, you still cannot predict which outcome you will get. The laws of physics themselves do not determine the outcome, they only determine the odds. This is a genuine change in what physics tells us about the world. Classical physics said the universe is deterministic. If you know everything about the present, the future is fixed. Quantum mechanics says no. Even with perfect knowledge of the present state, the future of any individual measurement is not determined. Only the probabilities are. This was deeply troubling to many physicists. Einstein famously resisted this conclusion. He felt that a theory providing only probabilities must be incomplete. There must be hidden variables, deeper information that quantum mechanics does not capture, that would restore determinism. He expressed this sentiment in his famous remark about God not playing dice. But decades of experiments have shown that Einstein was wrong on this point. Quantum mechanics is not incomplete in the way he hoped. There are no hidden variables of the simple kind he imagined that can reproduce all the predictions of quantum mechanics. We will come back to why we know this later. For now, the key point is that the Born rule, the rule connecting the wave function to probabilities, is not a reflection of our ignorance. It is a fundamental feature of the theory. The probabilities are not covering up a deeper deterministic reality. They appear to be built into the fabric of nature. Now let us talk about the uncertainty principle, because it is closely connected to everything we have been discussing, and it is widely misunderstood. Werner Heisenberg formulated the uncertainty principle in 1927. It states that certain pairs of properties cannot both be precisely defined at the same time. The most famous example is position and momentum. The more precisely you specify a particle's position, the less precisely its momentum can be defined, and vice versa. This is not about measurement disturbance. It is not that your instruments are too clumsy. It is not that looking at the particle with a photon kicks it and messes up its momentum. Popular accounts often frame the uncertainty principle this way, as though it is a practical problem of measurement. But that framing is wrong. The uncertainty principle is a consequence of what the quantum state is. It follows directly from the mathematics of wave functions. A wave function that is sharply concentrated in one location, meaning the particle has a fairly well-defined position, must be built from many different wavelengths. And in quantum mechanics, wavelength is directly related to momentum. Many wavelengths means a wide spread of possible momenta, which means momentum is poorly defined. Conversely, a wave function with a single well-defined wavelength, meaning the particle has a precise momentum, must be spread out across all of space. Its position is completely undefined. This is not a limitation of your measuring apparatus. It is a feature of the wave function itself. A quantum state that has both a perfectly defined position and a perfectly defined momentum simply does not exist. The mathematics does not allow it. Such a state would be a contradiction, like a square circle. The uncertainty principle is telling you something about the nature of quantum states, not about the quality of your instruments. Think about it this way. In classical physics, a particle has both a definite position and a definite momentum at every instant. Both properties are simultaneously real and precise. The uncertainty principle says this is impossible for quantum particles. There is no state in which both are exactly defined. This is not because of any measurement disturbance. It is because the quantum world is fundamentally different from the classical one. This connects directly to the question of what a particle is before measurement. Before you measure position, the particle does not have a definite position. Before you measure momentum, it does not have a definite momentum. And the uncertainty principle guarantees that these two indefinitenesses are linked. The more definite one becomes, the less definite the other must be. The particle exists in a quantum state that is intrinsically fuzzy with respect to both properties simultaneously. Not because we are ignorant, but because that is what the quantum state is. There is another profound aspect of the quantum formalism that deserves attention. It is called complementarity. Niels Bohr introduced this idea in the late 1920s, and it captures something essential about quantum mechanics. Complementarity says that certain descriptions of a quantum system are mutually exclusive. You can set up an experiment that reveals a particle's wave-like properties, like the interference pattern in the double-slit experiment. Or you can set up an experiment that reveals its particle-like properties, like detecting which slit it went through. But you cannot do both at the same time. If you detect the path, you destroy the interference. If you observe the interference, you cannot know the path. These are not just two different ways of looking at the same thing. They are two genuinely different experimental arrangements that give genuinely different kinds of results. And quantum mechanics tells you precisely what to expect in each case. It gives you the wave function, and the wave function tells you the probabilities for whatever measurement you choose to perform. But the choice of measurement matters. Different measurements on the same quantum state can reveal different, mutually exclusive aspects of the system. This is why asking, "What is the particle really?" is so tricky. If you measure position, you get a definite position. The particle looks like a localized point. If you measure momentum, you get a definite momentum. The particle looks like a spread-out wave. If you do the double-slit experiment without detectors, the particle shows wave-like interference. If you add detectors, it shows particle-like path behavior. The particle is not secretly one thing that appears different depending on how you look. The quantum state is the full reality, and different measurements access different aspects of that reality. The aspects are complementary. You can see one or the other, but never both simultaneously. Let us also address something that often confuses people: the role of the observer. Popular accounts of quantum mechanics sometimes claim that consciousness collapses the wave function, that the act of a human mind observing the result is what forces the particle into a definite state. This is misleading and almost certainly wrong. The experiments do not support the idea that human consciousness plays any special role. When we say measurement in quantum mechanics, we do not mean a human looking at something. We mean a physical interaction between the quantum system and a larger system, typically a macroscopic detector, that creates a record of the outcome. When an electron hits a detector screen and creates a flash of light, that is a measurement. The flash occurs whether or not anyone is watching. The wave function changes because of the physical interaction with the detector, not because a conscious mind observed the flash. There is nothing in the mathematical formalism of quantum mechanics that mentions consciousness or observers in any special way. The measurement problem, the question of what exactly constitutes a measurement and why measurements produce definite outcomes, is a genuine unsolved problem in physics. But the answer is almost certainly physical, not mental. It has to do with how small quantum systems interact with large, complex environments, not with whether a human being happens to be paying attention. So let us draw together what quantum mechanics actually says about a particle before measurement. Before measurement, the particle is described by a quantum state, a wave function. This wave function encodes everything there is to know about the particle. It does not describe our ignorance of a deeper reality. It is the deepest reality available. The wave function assigns probability amplitudes, complex numbers, to every possible outcome of every possible measurement. These amplitudes, when squared, give the probabilities of each outcome. Before measurement, the particle does not generally have a definite position, a definite momentum, or a definite spin in any given direction. It exists in a superposition of possibilities. These are not possibilities in the sense of things that might be true. They are possibilities in the sense of things that are all simultaneously encoded in the quantum state. The superposition is not a metaphor. It is a precise mathematical structure with experimentally testable consequences, like interference patterns. When a measurement is performed, one outcome occurs. The probability of each outcome is given by the Born rule. The outcome is fundamentally unpredictable in individual cases. Only the statistical distribution over many measurements is determined. After measurement, the quantum state has changed. It now reflects the outcome that occurred. But before the measurement, the outcome did not exist. It was not hiding. It was not predetermined. It came into being through the process of measurement. The uncertainty principle is not about clumsiness. It is about the nature of quantum states. Certain pairs of properties cannot simultaneously have definite values. This is a mathematical fact about wave functions, not a statement about laboratory equipment. Complementarity tells us that different experimental arrangements reveal different aspects of the quantum state. No single experiment reveals everything. The full picture requires multiple complementary perspectives, and those perspectives cannot all be obtained simultaneously. This is what quantum mechanics says. It is precise. It is mathematical. It is confirmed by every experiment ever performed. And it tells us something revolutionary about the nature of particles before measurement. They are not tiny objects with definite properties traveling along definite paths. They are quantum states, superpositions of possibilities governed by probability amplitudes, intrinsically indefinite in ways that no classical picture can capture. The wave function does not describe a thing sitting in space. It describes a set of potentialities, constrained by the mathematics of quantum theory, waiting for an interaction to actualize one of them. This is not nothing. Before measurement, the particle is not absent from reality. Something real is there. The quantum state is real in the sense that it has measurable consequences. It determines what you will observe and with what probability. It evolves in time according to precise mathematical equations. It can be manipulated, prepared, and transformed. It interacts with other quantum states in specific, predictable ways. It is as real as anything in physics. But it is not the kind of real that the classical worldview prepared us for. It is a new kind of real, a quantum kind. And that distinction between classical reality, where things have definite properties at all times, and quantum reality, where they do not, is not a philosophical preference. It is an experimental fact. The double-slit experiment, the Stern-Gerlach experiment, the Bell test experiments we will discuss later, decades of precision measurements across every domain of physics, all confirm the same conclusion. The classical picture of definite objects with definite properties is an approximation. A very good approximation at large scales, where quantum effects wash out, but an approximation nonetheless. At the deepest level, reality is quantum, and quantum reality does not offer the comforting certainty of the classical world. What it offers instead is something more honest, a precise framework that tells you exactly what can be predicted and what cannot. That distinguishes clearly between what the theory determines and what it leaves open. That gives you the probabilities without pretending the outcomes are predetermined. The quantum state is the most complete description of a particle before measurement that physics has ever produced. It is not everything we might want, but it is everything nature allows us to have. And understanding that, truly understanding it, is the first step toward grasping what a particle actually is before you look at it. Not a tiny ball, not a classical wave, not nothing, but a quantum state. A precisely described, experimentally confirmed, fundamentally indefinite piece of physical reality. Everything we have discussed so far treated particles as individual objects. A single electron fired through a double slit. A single spin measured in a Stern-Gerlach apparatus. A single quantum state described by a wave function. This is how quantum mechanics is usually introduced, and it works remarkably well for many problems. But it is not the deepest picture physics has to offer. There is a more fundamental framework underneath, one that changes not just what we think particles do, but what we think particles are. That framework is quantum field theory, and understanding it transforms the question of what a particle is before measurement into something even more striking. Let us start with a simple question. Where do particles come from? In the classical picture, particles just exist. They are given. You start with a collection of tiny objects, electrons, protons, photons, and you describe how they move and interact. The particles are fundamental ingredients placed into the universe from the beginning. Quantum mechanics, as we have described it so far, takes the same approach. You have an electron. It has a wave function. You calculate probabilities. But you never ask where the electron came from or what it is made of at a deeper level. You just accept that it exists and describe its behavior. Quantum field theory goes deeper. It says particles are not fundamental objects at all. They are not tiny things placed into space. Instead, what is fundamental is a set of fields. These fields are not like gravitational fields or magnetic fields in the classical sense, though they are related. A quantum field is a physical entity that exists everywhere in space, at every point, at every moment. It permeates the entire universe. There is an electron field, a photon field, a quark field, a neutrino field, and so on. One field for every type of particle. These fields are always present. They fill all of space. They never go away. A particle, in this picture, is not a separate object sitting in space. It is an excitation of the underlying field. Think of a calm lake. The water is everywhere, smooth and still. Now imagine a ripple on the surface. The ripple is not a separate object placed onto the water. It is a disturbance in the water itself. It is the water doing something, moving in a particular pattern. The ripple moves across the lake, carries energy, and eventually dissipates. But at no point is the ripple a separate thing from the water. It is the water in a particular state of excitation. An electron is like that ripple. The electron field exists everywhere. When the field is in its lowest energy state, its ground state, there are no electrons present. The field is calm. But when the field is excited in a specific way, when energy is added in the right pattern, that excitation is what we detect as an electron. The electron is the field, vibrating in a particular mode. It is not something placed into the field from outside. It is a disturbance of the field itself. This might sound like a subtle distinction, but it has enormous consequences. First, it explains why all electrons are identical. In the classical picture, each electron is a separate object. There is no fundamental reason why they should all have the same mass, the same charge, the same spin. They just do. It is an unexplained coincidence. But in quantum field theory, all electrons are excitations of the same underlying field. They are identical because they are different ripples in the same lake. A ripple on one side of the lake and a ripple on the other side are both just water moving. They have the same properties because they are made of the same stuff, configured in the same way. Every electron in the universe is a vibration of the same electron field. And that is why every electron has exactly the same mass, exactly the same charge, exactly the same magnetic moment, down to the last decimal place. Second, quantum field theory explains where particles come from and where they go. Particles can be created and destroyed. This happens constantly in nature. When a high-energy photon passes near a heavy nucleus, it can transform into an electron and a positron. Two particles created from pure energy. This is called pair production, and it is not a theoretical abstraction. It happens in laboratories every day. At particle accelerators like the Large Hadron Collider, protons are smashed together at enormous energies. The energy of the collision does not just rearrange the protons, it creates entirely new particles that did not exist a moment before. Quarks, gluons, electrons, muons, even the Higgs boson. All of them are produced from the concentrated energy of the collision. They flash into existence, live for a tiny fraction of a second, and then decay into other particles. In a single collision, dozens or even hundreds of new particles can appear. The reverse happens too. When an electron meets a positron, its antimatter counterpart, they annihilate. Both particles vanish completely. Their mass is converted entirely into energy in the form of photons. Two particles go in, 0 particles come out. Just light. The matter is gone. This is not science fiction. It is measured, calibrated, and used in medical imaging. A PET scan works precisely because positrons emitted by a radioactive tracer annihilate with electrons inside your body, producing pairs of photons that detectors pick up to create an image. Classical mechanics cannot explain any of this. If particles are fundamental objects, where do the new ones come from when they are created? Where do they go when they are destroyed? You cannot create a billiard ball from energy. You cannot destroy one and get light. But if particles are excitations of fields, creation and destruction are natural. Creating a particle means exciting the field. Destroying a particle means the field returning to a lower energy state. The field itself never appears or disappears. It is always there. Only the excitations come and go. The field is the permanent thing. The particle is the temporary thing. This is a complete inversion of how most people think about matter. Third, quantum field theory reveals something remarkable about empty space. In classical physics, empty space is truly empty. Remove all matter and radiation, and you have a vacuum. Nothing. But in quantum field theory, the vacuum is not nothing. It is the ground state of all the quantum fields. And because of the uncertainty principle, even in the ground state, the fields cannot be perfectly still. They must fluctuate. There are tiny, random vibrations in every field, everywhere, all the time. These are called vacuum fluctuations, or zero-point fluctuations. They are not particles. They do not carry energy that you can extract and use. But they are real, measurable physical effects. The Casimir effect is one demonstration of this. If you place two uncharged metal plates very close together in a vacuum, with nothing between them, they experience a tiny attractive force pushing them together. This force arises because the vacuum fluctuations between the plates are slightly different from those outside the plates. The geometry constrains which fluctuations can exist in the gap, and the resulting imbalance creates a measurable force. This was predicted in 1948 and has been confirmed experimentally with high precision. The vacuum is not empty. It is a seething quantum state of all the underlying fields. Now, combine this picture with what we learned about quantum states and measurement. Before you detect a particle, before any measurement occurs, what exists is the quantum field in some particular state. That state might be a superposition of different numbers of excitations. It might be entangled with other fields in complex ways. It might have amplitudes spread across vast regions of space. The field is there. It is real. It has a definite quantum state. But that state does not generally correspond to a definite number of particles at definite locations with definite properties. The particle picture, a specific number of little objects at specific places, only emerges when you perform a measurement, when a detector clicks, when something interacts with the field in a way that registers a definite count. This is a deeper version of the same lesson the double-slit experiment taught us. Before measurement, the electron is not a tiny ball at a definite location. Now we can say something even more precise. Before measurement, the electron field is in a quantum state that does not necessarily correspond to a single localized particle at all. The excitation is spread out. The field state is a superposition. The particle, as a definite localized object, comes into being through the act of detection. What exists before detection is the field, in its quantum state, carrying the potential for a particle to be detected, but not yet manifesting as one. Richard Feynman, along with Julian Schwinger and Shinichiro Tomonaga, developed the most precise version of quantum field theory in the late 1940s. Their framework, called quantum electrodynamics, or QED, describes how electrons and photons interact. It is the most accurately tested theory in the history of science. Its predictions for the magnetic moment of the electron agree with experiment to better than 1 part in 10 billion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. Nothing else in science comes close to this level of precision. And this extraordinary theory tells us that particles are not objects. They are field excitations. The electron you detect in your laboratory is a localized excitation of the electron field that permeates all of space. Between detections, between measurements, the field is in a quantum state that may not correspond to any definite number of particles at any definite locations. The field is real. The quantum state is real. But the particle, the thing you picture in your mind as a tiny dot flying through space, is an outcome of measurement, not a permanent feature of reality. Now, let us move to one of the most striking features of quantum physics, one that has no classical analogue whatsoever: entanglement. This is a feature of quantum states involving more than one particle, or more precisely, more than one excitation of the fields. And it reveals something about the nature of quantum reality that even Einstein found hard to accept. Imagine you have 2 electrons. In classical physics, the state of the system is just the combination of each electron's individual state. Electron 1 is here with this velocity. Electron 2 is there with that velocity. The whole is just the sum of the parts. Each particle has its own independent properties, and the system is described by listing them separately. Quantum mechanics allows something radically different. Two particles can exist in a joint quantum state that cannot be broken down into separate individual states. The particles are correlated in a way that has no classical explanation. This is entanglement. Here is a concrete example. You can prepare two electrons so that their spins are entangled. Specifically, you prepare them in a state where the total spin is 0. This means if one electron is measured to be spin up along some direction, the other will always be found spin down along the same direction, and vice versa. Always, without exception. No matter how far apart the two electrons are when you measure them. Now, remember what we said about superposition. Before measurement, neither electron has a definite spin. The spin of each electron, individually, is undefined. It is in a superposition of up and down. But the joint state of the two electrons is perfectly defined. It is the state with total spin 0. The two spins are correlated, even though neither one individually has a definite value. Here is why this is so disturbing. Suppose you separate the two electrons and send them to opposite sides of the planet, or opposite sides of the galaxy. Then you measure electron 1 and find it spin up. Instantly, you know electron 2 is spin down. Before you measured electron 1, neither electron had a definite spin. Both were in superpositions. But the moment you measure one, the other acquires a definite value. This happens regardless of the distance between them. It happens regardless of whether the measurement on electron 2 occurs 1 second later, 1 nanosecond later, or seemingly at the same instant. Einstein found this deeply troubling. He called it spooky action at a distance. He argued that it must mean quantum mechanics is incomplete. Surely, he said, the electrons must have had definite spins all along. The correlation was established when they were prepared together, and each electron carried its definite spin with it as it travelled. The measurement simply revealed pre-existing values, like opening two sealed envelopes that were prepared in advance. This is called a local hidden variable theory. The properties are hidden from us, but definite, and the correlations are local, established at preparation, not at measurement. Einstein's argument was powerful, and for decades it seemed like a philosophical disagreement that could never be resolved by experiment. Quantum mechanics predicted correlations. Hidden variables predicted the same correlations. Both theories seemed to agree on every measurable outcome. How could you ever tell which one was right? In 1964, physicist John Bell found the answer, and it was one of the most brilliant insights in the history of physics. Bell did not argue about philosophy, he did mathematics. He asked a precise question. If the electrons really do have pre-existing definite spins, assigned at the moment of preparation and carried along like sealed envelopes, then what are the strongest possible correlations you could ever see between the measurements on the two electrons? The key is that you can measure spin along different directions, not just vertical. You can tilt your measuring device to any angle. And when you measure the spins of many entangled pairs along various combinations of angles, you get a set of statistical correlations. Bell showed that if the spins are pre-existing and locally determined, these correlations must satisfy a mathematical constraint, a ceiling they cannot exceed. This is Bell's inequality. The logic is surprisingly intuitive once you see it. Imagine the two electrons really do carry definite spin values assigned when they were prepared. Each electron has a spin value for every possible measurement direction. It carries this information with it like a hidden instruction set. When you measure along a particular direction, you simply read off the pre-assigned answer. The correlations between the two electrons arise because their instruction sets were coordinated at preparation. They were made to be opposite, so measuring one tells you about the other. Now, Bell asked what happens when you measure the two electrons along different directions. Not the same direction, different angles. If both electrons carry fixed instruction sets, the correlations between measurements at different angles are limited. There is a maximum strength these correlations can reach. You can prove this rigorously with probability theory. No matter how cleverly you design the instruction sets, no matter how you coordinate them at preparation, the correlations are bounded. They cannot be arbitrarily strong. That bound is Bell's inequality. Quantum mechanics predicts correlations that violate this bound. According to quantum theory, the correlations between entangled particles measured at certain combinations of angles are stronger than any hidden instruction set could produce. Not by a tiny margin, by a clear, measurable amount. Bell's inequality is a line in the sand. Hidden variables stay below it, quantum mechanics goes above it, and you can test which one nature actually does. The experiments were performed, most famously by Arlan Aspect in the early 1980s, and later, with increasing precision, by many groups including Anton Zeilinger and John Clauser. All three, Aspect, Clauser and Zeilinger, shared the 2022 Nobel Prize in Physics for this work. The results are unambiguous. Bell's inequality is violated. The correlations between entangled particles are exactly as quantum mechanics predicts. They are stronger than any local hidden variable theory can explain. The electrons did not have definite spins before measurement. The correlations are not pre-established and carried along like sealed envelopes. Something genuinely quantum is happening. Over the decades, experimenters have closed every loophole that critics raised. What if the detectors are influencing each other through some unknown signal? Aspect's experiments placed the detectors far enough apart and switched their measurement angles fast enough that no signal traveling at the speed of light could connect them. What if the random choices of measurement angle are somehow correlated with the hidden variables? Later experiments used the light from distant quasars, photons that left their sources billions of years ago, to choose the measurement angles, ensuring the choices were made long before the entangled particles were even created. Every loophole tested, every loophole closed, the result stands. Nature violates Bell's inequality. Local hidden variables are ruled out. This does not mean information travels faster than light. You cannot use entanglement to send a message. The outcomes on each side, taken individually, look completely random. It is only when you compare the results from both sides that the correlations become apparent, and that comparison requires ordinary communication, which is limited by the speed of light. So relativity is safe. But the implication for reality is profound. Before measurement, the properties of entangled particles are not just unknown, they are undefined. And they are undefined in a correlated way that cannot be explained by any classical mechanism. Entanglement is not a statement about our ignorance, it is a feature of the quantum state of the world. Entanglement also connects directly to the field picture. In quantum field theory, the fields at different points in space are generally entangled with each other. The vacuum state itself, the state with no particles at all, is an entangled state. The field fluctuations at one location are correlated with the field fluctuations at nearby locations. This entanglement is built into the ground state of the fields. It is a fundamental feature of quantum field theory, and it has measurable consequences. The universe, at its most basic level, is a web of entangled quantum fields. Now let us address a question that naturally arises from everything we have discussed. If quantum mechanics says particles do not have definite properties before measurement, if superposition and entanglement are fundamental features of reality, then why does the everyday world look so definite? You never see a chair in a superposition of being in two places at once. You never notice your coffee mug entangled with a cup on the other side of the room. The classical world, the world of definite objects with definite properties, seems completely solid and reliable. If quantum mechanics is the fundamental theory, why does the world look classical? The answer is one of the most important discoveries in the foundations of quantum mechanics. It is called decoherence, and understanding it is essential to understanding what happens between the quantum world and the classical world we experience. Decoherence is not a new law of physics. It is a consequence of quantum mechanics applied to systems that interact with their environments. And its key insight is this: quantum superpositions are incredibly fragile. They are easily disrupted by interactions with the surrounding environment. When a quantum system interacts with a large number of other particles, air molecules, photons, thermal radiation, anything at all, the quantum state of the system becomes entangled with the quantum states of all those environmental particles, and that entanglement effectively destroys the interference effects that make quantum behavior visible. Let us make this concrete. Think about the double-slit experiment again. A single electron passes through two slits and produces an interference pattern on the screen. The interference arises because the quantum state of the electron passes through both slits simultaneously, and the two paths interfere. Now imagine that as the electron passes through the slits, it bumps into an air molecule. That interaction entangles the electron with the air molecule. The air molecule now carries information about which slit the electron went through. Not because anyone reads that information, not because anyone cares, but because the physical interaction created a correlation between the electron's path and the air molecule's state. Once that entanglement exists, the interference pattern vanishes, not because someone observed which slit the electron took, but because the environment now contains which path information. The two paths of the electron are no longer able to interfere because they are correlated with different states of the air molecule. The superposition has not been destroyed in any fundamental sense. The electron and the air molecule together are still in a quantum superposition, but the interference is now encoded in the joint state of the electron and the air molecule. To see it, you would need to measure both the electron and the air molecule simultaneously and look for correlations. In practice, that is impossible. The air molecule quickly interacts with other air molecules, spreading the entanglement further. Within a fantastically short time, the entanglement has spread to billions upon billions of environmental particles. The interference is still there in principle, encoded in the joint quantum state of the electron and its entire environment. But it is so thoroughly dispersed that no experiment could ever recover it. For all practical purposes, it is gone. This is decoherence. It does not collapse the wave function in any fundamental sense. It does not require a conscious observer. It does not add anything new to quantum mechanics. It is simply what happens when a quantum system becomes entangled with a large environment. The quantum superposition does not disappear from the universe. It becomes entangled with so many environmental particles that its observable effects vanish for any practical measurement on the system alone. The result is that the system appears to be in a definite classical state, even though the underlying physics is still quantum. The electron that bumped into the air molecule appears to have gone through one slit or the other, even though quantum mechanics never required it to choose. The appearance of classical definiteness is an illusion produced by entanglement with the environment. Not an illusion in the sense of being fake, but an illusion in the sense that the classical picture is an approximation. The deeper reality is still quantum. The superposition is still there. It is just inaccessible. This explains why the everyday world looks classical. Every object you interact with is constantly bombarded by photons, air molecules, thermal radiation, and countless other particles. Every object is constantly becoming entangled with its environment. A coffee mug on your desk is interacting with trillions of air molecules every second. Each interaction creates entanglement. The result is that any quantum superposition the mug might theoretically be in decoheres almost instantaneously. The timescale for decoherence of a macroscopic object at room temperature is absurdly short, far less than a trillionth of a second. There is no experiment you could ever perform fast enough to catch a coffee mug in a superposition. The environment destroys the interference before you could ever detect it. This is why Erwin Schrödinger's famous thought experiment about a cat that is simultaneously alive and dead is not really a paradox. Schrödinger proposed it in 1935 to highlight what he saw as an absurdity in quantum mechanics. If quantum mechanics allows electrons to be in superpositions, and if a cat's fate is tied to a quantum event, then the cat should be in a superposition of alive and dead. But we never see cats in such states. Does that mean quantum mechanics is wrong? Decoherence gives the answer. The cat is made of trillions upon trillions of atoms. It is in constant interaction with its environment. Air, light, the walls of the box, its own internal thermal radiation. Any superposition involving the cat decoheres almost instantly. The quantum state of the cat becomes entangled with the quantum state of its environment so rapidly that the superposition of alive and dead has no measurable consequences. The cat is effectively in one state or the other long before you open the box. Not because quantum mechanics stops applying to cats, it applies to everything, but because the environment forces the cat into an effectively classical state through decoherence. Decoherence does not solve every puzzle about quantum measurement. It explains why we do not see superpositions of macroscopic objects. It explains the transition from quantum to classical behavior. But it does not by itself explain why one particular outcome occurs rather than another. It tells you that the system will appear to be in one of the possible states, but it does not tell you which one. That question, why this outcome rather than that one, remains open. Different interpretations of quantum mechanics give different answers, as we will discuss. But decoherence does something essential for our understanding of what a particle is before measurement. It shows that the boundary between the quantum world and the classical world is not sharp. There is no magic size or mass above which things become classical. Everything is quantum. Electrons, atoms, molecules, baseballs, cats, planets, all are described by quantum states. All are subject to quantum mechanics. The difference is that large objects decohere almost instantly, so their quantum nature is hidden. Small isolated objects, like a single electron in a vacuum passing through a double slit, can maintain their quantum superposition because there is nothing around to entangle with and cause decoherence. This gives us a more complete picture of what exists before measurement. The fundamental objects are quantum fields, permeating all of space. These fields exist in quantum states that are generally entangled with each other and with their environment. What we call a particle is an excitation of one of these fields. Before measurement, that excitation does not have a definite position, a definite momentum, or even, in some cases, a definite existence as a single particle. The field state is a superposition. It carries the potential for specific outcomes, but the outcomes themselves come into being through measurement, through physical interactions that entangle the system with a macroscopic environment, causing decoherence and producing a definite classical result. The picture that quantum field theory gives us is not one of tiny objects flying through space. It is one of fields, spread out everywhere, existing in quantum states, entangled across vast regions, fluctuating even in the vacuum, and producing what we call particles only when something interacts with those fields in a way that registers a definite detection. Between detections, what exists is the field state, mathematically precise, experimentally consequential, and fundamentally unlike anything the classical world prepared us to imagine. This is not a counsel of despair. We are not saying reality is unknowable. We are saying reality is quantum. The fields are real. Their quantum states are real. The entanglement is real. The probabilities that emerge from the Born rule are real. Decoherence is real. All of this is experimentally confirmed physics. What is different from the classical picture is the kind of reality involved. It is not a reality of definite little objects sitting at definite locations. It is a reality of quantum states, superpositions, and entanglement. A reality where the definite properties we observe in everyday life emerge from a deeper quantum substrate through the mechanism of decoherence. The electron that will be detected on your screen is, before detection, a quantum excitation of the electron field. That excitation is described by a quantum state that is spread out, indefinite, and possibly entangled with other fields and particles. The excitation is real, the field is real, but the definite localized particle that you will see when the screen lights up does not exist yet. It will come into being at the moment of detection, when the field state interacts with the detector and decoherence renders the outcome effectively classical. What is there before you measure? The field, in a quantum state, carrying probabilities, entangled with its surroundings. Not nothing, not a classical object, something real, but something new, something that centuries of classical thinking never anticipated, and something that modern physics has described with greater precision and confirmed with greater accuracy than any other description of nature in human history. We have come a long way. We started with the classical picture of particles as tiny objects with definite properties, and we watched it collapse under the weight of experimental evidence. We saw that quantum mechanics replaces that picture with something radically different, a wave function, a quantum state that does not assign definite positions or definite momenta, that carries probabilities instead of certainties. We went deeper still into quantum field theory, where particles are not objects at all, but excitations of underlying fields. Fields that permeate all of space, fluctuate even in the vacuum, and become entangled across vast distances. And we saw how decoherence explains why the everyday world looks classical, even though the fundamental physics is quantum. Now we need to confront the hardest part of the story. What does all of this actually mean? What is the quantum state really telling us about the nature of reality? And where does the established, confirmed physics end and genuine interpretation begin? Let us start by being very precise about what is settled. What follows is not controversial among physicists. It is confirmed by decades of experiments across every area of physics. Every laboratory in the world that does quantum mechanics relies on these facts daily. First, quantum systems are described by quantum states. These states evolve in time according to the Schrödinger equation, a precise mathematical rule that is deterministic. Given the quantum state at one time, the equation tells you exactly what the quantum state will be at any later time. There is no randomness in how the quantum state evolves between measurements. The evolution is smooth, continuous, and perfectly predictable. Second, when a measurement is performed, the result is one of a set of possible outcomes. The probability of each outcome is given by the Born rule. These probabilities are confirmed experimentally to extraordinary precision. Third, after the measurement, the quantum state changes to reflect the outcome that was observed. Fourth, the uncertainty principle limits what pairs of properties can be simultaneously well defined. This is a consequence of the mathematical structure of quantum states, not a limitation of instruments. Fifth, entanglement is real. Particles can exist in joint quantum states where the properties of each particle individually are undefined, but the correlations between them are perfectly defined. Bell test experiments confirm that these correlations cannot be explained by any local hidden variable theory. Sixth, decoherence explains the emergence of classical behavior from quantum mechanics. When a quantum system interacts with a large environment, the superposition becomes entangled with the environment, and the interference effects become practically unobservable. All of this is physics, tested, confirmed, operational physics. Physicists use these principles every day to design lasers, build semiconductors, develop quantum computers, predict the outcomes of particle collisions, and calculate the properties of materials. The framework works. It has never failed a single experimental test. But there is a question the framework does not answer, or more precisely, a question about which the framework is silent. When the measurement occurs and one outcome is obtained, what actually happened? Why did that particular outcome occur and not one of the others? The Schrödinger equation, which governs how quantum states evolve, does not describe a sudden jump to one outcome. It describes smooth, continuous evolution. If you apply it to the measurement process itself, treating the detector as a quantum system interacting with the particle, the equation predicts that the detector should end up in a superposition of having recorded all possible outcomes simultaneously. Not one outcome, all of them. But that is not what we observe. We observe one outcome, one click of the detector, one flash on the screen, one number on the readout. The Schrödinger equation, applied consistently to everything, including the measuring device, seems to predict something we do not see. Superpositions of measurement results. This is the measurement problem, and it has been an open question since the very beginning of quantum mechanics. Decoherence helps enormously. It shows that the interference between different outcomes becomes unobservable almost instantly for macroscopic detectors. After decoherence, the quantum state of the system plus environment looks, for all practical purposes, like a classical mixture. A situation where one outcome occurred, you just do not know which one yet. Decoherence explains why you never see the superposition, but it does not, by itself, explain why one particular outcome is realized. The mathematics still describes all outcomes existing in the entangled state of system and environment. Decoherence suppresses the interference between them, but does not eliminate any of them from the quantum state. This is where interpretation enters. Different interpretations of quantum mechanics give different answers to the measurement problem. And here is what is crucial to understand. These interpretations do not differ in their experimental predictions. They all use the same mathematical formalism. They all predict the same probabilities for the same experiments. You cannot design an experiment that distinguishes between them. At least, no one has found one yet. They differ in what they say about what is happening behind the predictions. They differ in their ontology, their picture of what exists. Let us look at several of the most important interpretations. Not to turn this into a survey or a debate, but because understanding what they agree on and what they disagree about reveals exactly where the boundary between established physics and open questions lies. The Copenhagen interpretation, associated primarily with Niels Bohr and Werner Heisenberg, is the oldest and most widely taught. In its most careful formulation, it says something like this: the quantum state is a tool for calculating the probabilities of measurement outcomes. It is the most complete description available. You should not ask what the particle is doing between measurements, because the theory does not answer that question, and the question may not have a meaningful answer. Measurement is a fundamental concept that cannot be fully analyzed within quantum mechanics. When a measurement occurs, one outcome is obtained, and the quantum state is updated accordingly. That is all there is to say. Copenhagen is pragmatic. It tells you to use the formalism, trust the predictions, and stop asking questions the theory cannot answer. Many working physicists adopt something close to this attitude. It is effective. You can do excellent physics without ever worrying about what the wave function really is. But Copenhagen has critics. It seems to draw an arbitrary line between the quantum system and the measuring device. It says measurement produces a definite outcome, but does not explain why or how. It treats the classical world of measuring devices as fundamental rather than derived. And it refuses to say what the quantum state represents, which strikes many physicists and philosophers as unsatisfying. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says the Schrödinger equation is the complete and exact law governing all quantum systems at all times, including during measurement. There is no collapse. There is no special role for measurement. When a measurement occurs, the quantum state evolves smoothly into a superposition of all possible outcomes, exactly as the Schrödinger equation predicts. And all of those outcomes are real. the universe splits. In one branch, the detector recorded spin up. In another branch, the detector recorded spin down. Both branches exist. Both are equally real. You, the observer, also split. One version of you sees spin up. Another version sees spin down. Each version is unaware of the other because decoherence prevents the branches from interfering with each other. Many worlds is mathematically elegant. It takes the Schrödinger equation seriously and applies it universally, without exceptions. It eliminates the measurement problem by eliminating collapse. But it comes at a staggering cost. It requires an ever-branching tree of parallel realities, each as real as the one you experience. Most physicists find this ontologically extravagant. Others argue it is simply what the mathematics says, and our discomfort is irrelevant. The interpretation also faces technical challenges, particularly in explaining why the Born rule gives the correct probabilities. If all outcomes occur, what does it mean to say one outcome has a higher probability than another? Everett and his followers have proposed answers, but the debate continues. The pilot wave theory, developed by Louis de Broglie in 1927 and later refined by David Bohm in 1952, offers yet another picture. It says particles do have definite positions at all times. There are real particles following real trajectories through real space. But these trajectories are not classical. They are guided by the wave function, which acts as a pilot wave, pushing the particles along specific paths. In the double-slit experiment, each electron goes through one slit, not both. But the pilot wave goes through both slits and creates an interference pattern that guides where the electron lands. Over many electrons, the guided trajectories reproduce the interference pattern exactly. Pilot wave theory restores determinism. If you know the exact initial position of every particle and the exact wave function, you can predict every future outcome precisely. The randomness in quantum mechanics arises because we do not know the exact initial positions. The theory reproduces all the predictions of standard quantum mechanics, while maintaining that particles have definite positions at all times. But pilot wave theory has its own costs. It requires a wave function that is a real physical field guiding particles. This wave function exists in a high-dimensional configuration space, not in ordinary three-dimensional space. For a system of two particles, the wave function lives in a six-dimensional space. The three particles, 9 dimensions. For a system of 10 to the 23 particles, the wave function lives in a space with roughly 10 to the 23 dimensions. This is an extraordinarily complex object to accept as physically real. The theory is also non-local. The pilot wave connects all particles simultaneously, so a measurement on one particle instantaneously affects the guidance of distant particles. This non-locality is consistent with the Bell test results, which prove that any hidden variable theory reproducing quantum predictions must be non-local. But it makes some physicists uncomfortable. There are other interpretations as well. Objective collapse theories, like the GRW theory developed in the 1980s, propose that the wave function does undergo real physical collapse, but not because of measurement. Instead, collapse happens spontaneously and randomly at a very low rate for individual particles. For a single electron, spontaneous collapse is incredibly rare, so the electron maintains its superposition for a very long time. But for a macroscopic object made of trillions of particles, the sheer number of particles means that at least one of them collapses almost instantly, and that collapse drags the entire object into a definite state. GRW modifies the Schrödinger equation slightly, adding a stochastic collapse term. This means it actually makes different predictions from standard quantum mechanics, though the differences are extremely small and have not yet been detected. experiments are being designed to test them. Relational quantum mechanics, developed by Carlo Rovelli, proposes that quantum states are not absolute. They are relative to the observer. Not a conscious observer, but any physical system. The quantum state of a particle as described by one system might be different from the quantum state as described by another system. There is no view from nowhere, no absolute quantum state of the universe. All quantum descriptions are relational, defined between pairs of interacting systems. This interpretation dissolves the measurement problem by denying that there is a single objective quantum state that needs to collapse. Different systems have different descriptions, and those descriptions are consistent whenever the systems interact. Each interpretation offers a different answer to the question of what a particle is before measurement. In Copenhagen, the question has no answer, because the formalism does not address it. In many worlds, the particle is in a superposition that never collapses, and all outcomes are real in different branches. In pilot wave theory, the particle has a definite position at all times, guided by a real wave function. In objective collapse theories, the particle is in a superposition that collapses spontaneously at random. In relational quantum mechanics, the state of the particle depends on who is asking. These are very different pictures of reality. And here is the remarkable thing. They all make the same experimental predictions, at least for all experiments we have performed so far. You cannot currently distinguish between them by doing experiments. The choice between them is currently a matter of philosophy, aesthetics, and theoretical preference, not empirical evidence. This might seem frustrating. You might want to know which one is right. But the fact that multiple, internally consistent interpretations exist, all compatible with the same experimental evidence, tells us something important about the nature of the question. The question, what is the particle really doing before measurement, goes beyond what current experimental evidence can answer. The evidence tells us what happens when we measure. It tells us the probabilities. It confirms entanglement, superposition, and decoherence. But it does not uniquely determine the underlying ontology.
Now, this does not mean the question is meaningless. It does not mean all interpretations are equally good. Physicists and philosophers have strong arguments for and against each one, and it is possible that future experiments or future theoretical developments will favour one interpretation over others. The GRW collapse theory, for instance, makes slightly different predictions that might be testable with improving technology. Some researchers are designing experiments to test whether gravity might cause wave function collapse, as Roger Penrose has proposed. Others are working on quantum gravity, where the choice of interpretation might have concrete physical consequences. The question is open, not closed. It is an active area of research, not a settled debate. But regardless of which interpretation is ultimately correct, certain things are clear, and these things are far more important than the interpretive debates. Before measurement, a particle in quantum physics is not a tiny classical object with a definite position and a definite trajectory. This is not an interpretation. This is an experimental fact. The double-slit experiment, the Bell tests, the precision measurements of quantum electrodynamics, all of these confirm that the classical particle picture is wrong. No interpretation of quantum mechanics restores the classical picture. Even pilot wave theory, which gives particles definite positions, requires a non-local pilot wave that is fundamentally unlike anything in classical physics. Before measurement, what exists is a quantum state. This state is real in the sense that it has measurable consequences. It determines probabilities. It exhibits interference. It supports entanglement. It evolves according to precise mathematical laws. It is the most complete description of the particle that physics can provide.
Whether you call that state a wave function, a quantum field excitation, a branch of the universal wave function, or a relational description between systems depends on your interpretation. But the state itself and its mathematical properties are interpretation independent. Before measurement does not mean nothing exists. This is a point worth emphasizing because it is easy to misunderstand quantum mechanics as saying particles blink into existence only when observed. That is wrong. The quantum fields exist. The quantum state exists. The probabilities are determined. Something physical and real is there. It is just not the kind of thing the classical world taught us to expect. It does not have the properties we associate with objects. It does not have a definite location. It does not follow a definite path. It does not carry fixed values of every measurable quantity. But it is not nothing. It is something new. Equally, before measurement does not mean a classical object exists, but we just cannot see it. This is the hidden variable intuition, and the Bell tests have ruled out the simplest versions of it. Whatever exists before measurement is not a tiny ball with definite properties that are merely hidden from us. The correlations between entangled particles are too strong for that. Nature itself is indefinite in a way that cannot be explained by ignorance of definite underlying values. This matters far beyond philosophy. The question of what a particle is before measurement is not an idle puzzle for academics. It connects to the deepest open problems in physics, and the most profound of those connections is to the problem of quantum gravity. General relativity, Einstein's theory of gravity, tells us that space-time is not a fixed stage on which physics plays out. It is a dynamic physical entity. Mass and energy curve space-time. That curvature is what we experience as gravity. The Earth orbits the Sun not because an invisible force pulls it, but because the Sun's mass curves the space-time around it, and the Earth follows the straightest possible path through that curved geometry. Space-time is not the background, it is part of the physics. It bends, stretches, and responds to the matter and energy within it. Now, if space-time is a physical system, and if every physical system is ultimately quantum, then space-time itself must be described by a quantum state. It must obey the rules of quantum mechanics. And that means space-time, like an electron, would not have definite properties before measurement. The geometry of space, the distance between 2 points, the rate at which a clock ticks, these would not be fixed values. They would be encoded in a quantum state, a superposition of different geometries, different distances, different curvatures, all simultaneously present in the quantum description, with no single geometry being the real one until something forces a definite outcome. Think about what that means. In quantum mechanics, before you measure an electron's position, there is no definite position. In quantum gravity, before something measures space-time's geometry, there would be no definite geometry, no definite distance between here and there, no definite answer to how much time passes between one event and another. The very concepts of distance and duration, the concepts we use to define what space and time are, become indefinite, fuzzy, subject to the same quantum rules as the spin of an electron. This creates a profound problem. All of quantum mechanics, as we currently formulate it, assumes a definite background spacetime. The Schrödinger equation evolves quantum states in time. But if time itself is in a quantum superposition, what does it mean to evolve in time? The wave function is defined across space. But if space itself has no definite geometry, what does it mean to be spread across space? The framework we use to describe quantum physics assumes the very thing that quantum gravity tells us cannot be assumed: a definite space-time. This is why the question of what exists before measurement is not academic. It is the central obstacle to building a quantum theory of gravity. Every approach to quantum gravity, whether string theory, loop quantum gravity, or any other framework,
must eventually answer the question we have been asking throughout this entire journey. What is the physical meaning of a quantum state before measurement, when the thing in the quantum state is space-time itself? Until that question is answered, a complete theory of quantum gravity remains out of reach. It connects to quantum computing. A quantum computer exploits superposition and entanglement to perform calculations that classical computers cannot. The power of quantum computing comes directly from the fact that quantum bits can exist in superpositions of 0 and 1 simultaneously. Understanding what that superposition means, physically, is not just a philosophical luxury. It guides how we design quantum algorithms, how we protect quantum information from decoherence, and how we think about the limits of computation. It connects to the nature of information. Quantum mechanics has revolutionized our understanding of information. Classical information is definite. A bit is either 0 or 1. Quantum information is different. A quantum bit can be in a superposition, and quantum information obeys different rules than classical information. You cannot copy it perfectly. You cannot measure it without disturbing it. Entanglement allows correlations that classical information cannot support. Understanding what quantum states are, what they represent about reality, is essential to understanding what information is at the most fundamental level. And it connects to the oldest and deepest question in physics. What is the universe made of? For centuries, the answer seemed clear: matter and energy. Tiny particles moving through space under the influence of forces. But quantum mechanics and quantum field theory have revealed that this picture is too simple. The universe is made of quantum fields in quantum states.
Those states are entangled, superposed, and fundamentally indefinite until measured. The definite classical world we experience emerges from this quantum substrate through decoherence. But the substrate itself is something new, something that does not fit neatly into the categories of classical thinking, something we are still learning to understand. So what is a particle before you measure it? Here is the most honest answer physics can give. Before measurement, a particle is a quantum state of an underlying quantum field. That state is described precisely by the mathematical formalism of quantum mechanics and quantum field theory. It determines the probabilities of all possible measurement outcomes. It can be in a superposition of different values for any given property. It can be entangled with other quantum states across arbitrary distances. It evolves in time according to exact mathematical laws. And it does not, in general, correspond to a tiny object at a definite location with definite properties. Something real is there. The quantum state is real. The field is real. The probabilities are real. But the definite particle, the thing with a position and a velocity and a path, is not there. Not yet. That comes later. That comes when the quantum state interacts with a macroscopic environment, when decoherence occurs, when a measurement produces a definite outcome. Before that, the particle is a potentiality. Not nothing, not a classical object, a quantum potentiality, described with more precision and confirmed with more accuracy than any other description in the history of science. The fact that this answer is uncomfortable says more about us than about nature. We evolved in a classical world. Our brains are wired to think in terms of objects with definite properties. When we close our eyes, we assume the world is still there, unchanged. And it is, at the scale of everyday life, because decoherence ensures that macroscopic objects behave classically. But at the fundamental level, the level of particles and fields, the world is not like that. It is quantum. And quantum reality is different from classical reality in ways that our intuitions cannot easily absorb. But that is what makes this question so important. It forces us to confront the limits of our intuition, to recognize that the universe is not obligated to make sense to brains that evolved to track predators and find food on the African savanna. The universe is what it is. And what it is, at the deepest level we have been able to probe, is quantum. The theory tells us what to expect when we measure,
It tells us the odds. It describes the states and the fields and the entanglement with breathtaking precision. What it does not tell us, not yet, is the full story of what those states represent in the fabric of reality. That question remains open. And that openness is not a failure of physics. It is the frontier of physics. The place where the deepest questions still live. The place where the next great breakthrough might emerge. A century ago, the double-slit experiment shattered the classical picture of particles and launched one of the greatest intellectual adventures in human history. That adventure is not over. We have learned an extraordinary amount about the quantum world. We have confirmed its predictions to unimaginable precision. We have built technologies on its principles that would seem like magic to previous generations. But the deepest question, what is actually there before you look, remains one of the most profound and honest open questions in all of science. And perhaps that is fitting. The universe has never been in the business of making itself easy to understand. It offers clues. It responds to experiments. It submits to mathematical description. But it does not hand over its deepest secrets easily. Quantum mechanics has given us the most powerful and precise framework ever devised for predicting the behavior of the physical world.
It has told us that reality at its foundation is stranger, richer, and more subtle than anything classical physics imagined. And it has left us with a question. What is a particle before you measure it, that might take another century or another revolution in physics to fully answer? That is not a disappointment. That is the sound of science working exactly as it should, pushing against the boundary of understanding, one experiment at a time, one question at a time, reaching deeper into the structure of reality than any generation before. And that journey, the journey toward understanding what the universe actually is at its most fundamental level, is far from over.